Stanford University.
Okay. All right, so I figured I have to start with a review because I do understand it's been 2 quarters since you last had lectures from me on quantum mechanics. On the other hand, they can't spend the whole quarter doing that. What I want to spend the quarter on is the applications of quantum mechanics, not the technology, but the physics problems. And the basic physics problems that I want to go through this quarter are those for which quantum mechanics was originally discovered, invented by Einstein, Heisenberg, Schrödinger, Pauli, all those people, namely atoms, electrons. I'm going to do atoms first. And you say, how can I do atoms first before I do electrons? Electrons are part of atoms. It's all right, we'll do a little bit about electrons, just almost nothing, but just enough to be able to write down the basic equations of the hydrogen atom, discuss the hydrogen atom a little bit, and then move on to further investigations of the electron. And when we say the electron, we're actually studying a class of particles, not just electrons, a wide class of particles which behave like electrons, which include mu particles, quarks, other things like that, and then the photon. So it's going to be atoms, electrons, and photons, but one of the themes that will recur is symmetries. Symmetries of nature and how symmetries are realized in quantum mechanics, how symmetries are represented in quantum mechanics, and what they tell us about the quantum mechanical system. Symmetries in quantum mechanics are an extremely powerful tool, which I'm going to tell you what a symmetry is. If you don't know what a symmetry is, it's okay at the moment. But let's begin with a very, very lightning review of the last quarter of quantum mechanics. First of all, the whole story begins by asking, how do you represent the state of a system? We could go back a step and ask, what is a system? But I'll assume you know what a system is. And how do you represent the states of a system? In classical mechanics, the states of a system are represented as points in phase space. In quantum mechanics, they're represented by state vectors. The idea of a vector is not a vector like a pointer in space pointing in a certain direction in space. It's an abstract notion. You can add vectors. You can multiply them by constants. And the mathematical structure of a state vector is a mathematical vector in a vector space. The vector space is not 3-dimensional, except in special cases. It could be any dimensional. So we represent states by state vectors, and the symbol for a state vector is Dirac's ket symbol, ket, K-E-T, which is the latter half of the term bracket, like bracket or bracket. Every state can be either represented by a ket vector or by a corresponding bra vector. Together, we often put them together to form a bracket, or a bracket. The bra vectors are in one-to-one correspondence with the ket vectors, and you should really think of them roughly as being the complex conjugates, in the same sense as complex conjugates of complex numbers. Complex numbers are ubiquitous in quantum mechanics, and so are complex vectors. So state vectors are represented by, or states are represented by state vectors. The state vectors, well, we could say a little bit more, but if I were to say the whole thing, of course, we would then go through the entire quarter, so I won't. In addition, there are observables, things that you measure. Measurables or observables. In classical mechanics, there are also observables. They're the things you measure, but we don't spend a lot of time talking about their mathematical structure. We just assume you know what I'm talking about when I say position of a particle is measurable, or momentum of a particle, or the energy of a particle, or whatever. In quantum mechanics, we have to be very precise what we mean by an observable. And observables are represented by linear Hermitian operators. I'll label them with, what are these? Let's see. These are Greek letters. What kind of letters are those? English? Roman? Latin? I don't know. By Latin, Yeah, it's true, it's capital alpha. Okay, but Latin letters are representing observables, and they are Hermitian operators that act on the vectors. Hermitian, for our purposes, translates or is the quantum mechanical equivalent of real. Real as in real or complex or imaginary. They are the real operators, which are equal to their own Hermitian conjugate. Every such operator in the space of states is called an observable, and presumably there is really a way to observe it. The eigenvalues and eigenvectors of these Hermitian operators play a special role. So let me just remind you, what is an eigenvalue and an eigenvector? If you have a Hermitian operator, you can search for vectors. Let's label the vector, let's label it little a, or better yet, alpha, since we want to label it with a Greek index. Let's label it with an alpha, and A, being an operator, can act on alpha, and alpha is an eigenvector of A if the action of A is just to multiply the vector alpha by a number. In this case, I'll use a redundant notation, the same notation for the eigenvalue and the eigenvector. And this says that the eigenvalue, the eigenvector alpha, is an eigenvector of A with eigenvalue alpha. And the significance of that equation is that, first of all, the set of eigenvalues of an operator or of an observable are the set of possible results of measurement. If you have a quantity which, when you measure it, can take on the value 1, 3, and 7, then the eigenvalues of that operator are 1, 3, and 7, and so forth. The eigenvectors are the state vectors of the system for which, if you make a measurement, the answer is definite, not statistical, determined, deterministic, and the answer to the measurement is alpha. Okay, so I assume you all remember this. I'm doing this mostly to just refresh your memory. Okay. Now, the particular systems we're going to be discussing mostly in this quarter are systems of particles. Particles are largely characterized by saying they're things which have a location in space, an ordinary location in space. For example, if space is one-dimensional, then a particle is a thing which has a coordinate x. It's located somewhere as an x. If space is three-dimensional, then particles move around. They have x, y, and z, and so forth. Let's write formulas for the case of one dimension, but I'll tell you what to do for 3 dimensions in a moment. Okay. Oh, sorry, let's come back. One point that I need to emphasize. For every bra and every ket, let's call the bra, let's call it phi. It is not necessarily the particular bra that goes together with psi, with the ket psi. For every pair like that, there is an inner product. There is a number. That number is in general a complex number, and it is represented as the inner product, and it's a number. It's a number for every pair of vectors. It represents a kind of product of the two vectors. It's similar in its mathematical structure to the dot product between two vectors in ordinary space, but it's a more abstract object. It's the inner product between two vectors, and it plays an important role in the logic of quantum mechanics. In particular, if two states are distinguishable uniquely by the property that there's some observable that you could measure which would be different in the two of them. Let's suppose there's some quantity that you could measure, and it is definite that the answer in the state psi is different than the state phi, then we would say those two states are distinctly different. There's no chance of confusing them. There's a measurement you could do to distinguish them. Then those states are said to be orthogonal. Orthogonal means physically identifiably different, and mathematically it's the statement that the two vectors have inner product equal to 0. So orthogonality is a fundamental property of relationships between vectors which says that they are different. You can't confuse them. Well, you can confuse them, but you shouldn't confuse them. Okay. Now, when it comes to particles, the most important observable is the position of a particle. And so let's just discuss particles moving on a line. A line is the x-axis. The location of the particle is just a value of x, and obviously x should be thought of as an observable. Okay. In particular, there are states which are labeled by a value of position. Let's call it x0. This is the point x0 over here. I'm just using the naught here to indicate a particular position. There are states which are labeled by x0, which have the property that if you measure the particle's position, you will definitely find it at x0. Okay. Good. The next concept, and of course, state vectors for different values, let's call them x and x prime. If x and x prime are two different positions, x and x prime, then clearly those two states are distinguishable operationally, and by measurement they're distinguishable, so these two states are orthogonal. Now, take any state whatever of this particle, call it psi, its inner product with the state representing the particle at x is called the wave function. The wave function of the particle, and it's written as psi of x. It's the psi that goes into the Schrodinger equation. It's Schrodinger's psi. I believe that Schrodinger was the first one to call it psi, psi. And the meaning of the wave function is closely related to, but not the same, as the probability that the particle is at position x. Psi of x is an arbitrary function. Well, it's not completely arbitrary, but let's say it's some function. What does it represent, psi of x? Psi of x is closely related to the probability to find the particle at position x, but it's not quite that. The probability itself, let's call it p of x, is the product of the wave function times its complex conjugate. The wave function times its complex conjugate is positive. Any number, any complex number times its own conjugate is always positive. Probabilities are always positive. Psi of x's are generally complex numbers. They can be positive, they can be negative, they can be imaginary, they can be whatever you like. So it would not make sense to say that psi is a probability, but it does make sense to say psi times psi star is a probability. Good, all right, that's the most important property of a particle, that it has a position. It has eigenvectors which represent particles of known position. And we can construct, of course, a position operator. A position operator just multiplies psi of x by x itself, by x. All right, so that's the idea of position. The other important observable for a particle, there are many, of course, there are many observables for a particle, but the other particularly important one is called the what? The momentum. The momentum. In classical mechanics and in quantum mechanics, positions and momenta come together. Oh, before we do that, I should discuss the issue of a particle moving not just in one dimension. What happens if a particle is moving in 3 dimensions? In other words, like a real particle. Then it has 3 observable positions, the 3 components of its position, namely x, y, and z, if you like. But since you can rotate axes, you can just think of the position as a point in 3-dimensional space. In that case, we would just think of x here as a point in 3-dimensional space. We could fill it out. We could fill out the equations by saying there are states which represent particles at known locations in 3 dimensions, x, y, and z. This represents a particle located at a point in 3-dimensional space, over here, x, y, and z, and the rules would be similar, very similar. The inner products of x prime, y prime, z prime, that would be 0 if there's any mismatch, not if x is not equal to x prime and y is not equal to y, but if the entire point x, y, z is not the same as the point x prime, y prime, z prime, then these are observably different positions for a particle, and the states are orthogonal to each other. I'm going to suppress the y and z, but keep in mind that the position of a particle depends on the dimensionality of the space that we're talking about, and in the real world, space is 3-dimensional. Okay, for each component of position, there is also a component of momentum. In classical physics, for non-relativistic classical physics, the momentum is just the mass times that component of the velocity. In quantum mechanics, the momentum is also observable and is also represented by an operator, by a Hermitian operator. Hermitian operators can be thought of in the abstract as objects which act on mathematical vectors, the space of states, or they can be thought of more concretely as operations on wave functions. Either one, you can think of them concretely as operations that what about x itself? What is the operation that represents the operator x? Well, it's just taking the state vector, psi of x, or taking the wave function, and multiplying it by x. If psi of x is a function representing the probability amplitude, psi of x is called the probability amplitude, or the wave function of a particle, then if you want to apply the operator representing position to psi of x, you just multiply psi of x by x. That's all. The eigenvectors of x are the wave functions which are highly peaked, very, very narrow Dirac delta functions. All right, in the same way, the momentum operator, now I'm not going to explain this in detail. For this, you go back to the lecture notes or to the lectures themselves. What lecture was it that we talked about momentum? Anybody remember? Art?
Several of them, but I think around 8.
Around 8? Yeah. Eight was, that's right. I remember with great grief, lecture 8, right? Okay. So the momentum of a particle is represented by an operator called P, and P also does something to psi of x. What it does to psi of x is it differentiates it. It differentiates it with respect to x, but not quite. The real thing is that it multiplies it by minus I, the complex number I. There's a factor of Planck's constant, h bar, and then it differentiates psi, d by dx, psi of x. That is the operator that acts on wave functions that represents the observable momentum. Everybody remember this? Yeah, we went through it. Okay, now, what about the eigenvectors of momentum? The eigenvectors of position are Dirac delta functions. They are functions which are zero everywheres except at the eigenvalue position. In other words, the eigenvector representing a particle known to be at x naught is a function which is zero everywheres except at x naught, where it's very high and very narrow. Let's not worry about its precise mathematical definition. It's called a Dirac delta function. And it's not too hard to believe that if the wave function of a particle is so concentrated at a particular point that the probability for finding it is zero everywhere except at that point. That, of course, makes sense. Now, what are the states for which the momentum is certain? In other words, what wave functions correspond to particles with definite momentum? And those are gotten by solving the eigenvalue equation. The eigenvalue equation is that P, whatever it is, in fact, we know what it is. Well, let's write the formal, let's write the abstract equation first, that P on psi is equal to little p naught times psi, the eigenvalue being little p naught. Little p naught is the value of momentum that this particle has, and in this particular state, the momentum of the particle is known to be p naught. This equation translates, just replacing p by minus I h bar d by dx, minus I h bar d psi by dx is equal to p naught, the number, a numerical number, times psi of x. Psi is a function of x, psi of x. And this is easy to solve. This is one of these equations which says that the derivative of something is proportional to that same thing. Derivative of psi, apart from a numerical number, the numerical number we could get rid of the I h bar on this side, it would reappear on this side. This is the equation of the type that represents an exponential. The derivative of something is proportional to something itself, and the solution of it is e to the I p naught x divided by Planck's constant. Now, I often get very tired of writing Planck's constant, and I often just set it equal to 1. We'll sometimes do that. In fact, I'll try to track it for the time being, but later on I may just drop it. And I think by the time I do drop it, I will have done it enough times that you'll know where the right place where it goes.
Question.
Yeah.
In the two equations you just wrote there, the upper one with the cats, that would say that those are, or that's a eigenvector.
Yeah, that says that eigenvector, that psi is an eigenvector of p with eigenvalue p naught.
But the one below holds for any wave function, right?
You think any wave function is e to the I px? Here? No, most wave functions don't satisfy this equation. No. In fact, it's true for basically this wave function. Okay. Now you'll notice, of course, that there's a huge difference between the eigenvectors of position, which are these narrow little spiky functions, and the eigenvectors of momentum. In particular, let's take the probability that's associated with e to the I p naught x. That's multiply it by its own complex conjugate. What happens if you multiply this by its own complex conjugate? You get 1. E to the I something times e to the minus I something is just plain 1. So this wave function, the one which represents a particle with a definite momentum, its probability distribution is smeared out over the entire line. By complete contrast, the eigenvector of a particle located at a definite position is highly concentrated, infinitely narrow. And this, of course, is a manifestation of the uncertainty principle. If you know the momentum of a particle, then its position is completely uncertain. And likewise, if you know the position of a particle, its momentum is also completely uncertain. I'll refer you back to the lecture notes for that purpose. That's basically quantum mechanics in a nutshell.
Question, please. I'm a little bit confused. I thought you said this, we know it's P0, so it's known. But
yeah, the momentum is known. The momentum is known.
Momentum. Right. But then when you try to calculate the probability of this...
No, the probability for position. Given that the momentum is P naught, now an experimenter is going to do an experiment not to check its momentum, but is going to do an experiment which measures its position. 2 different kinds of experiments.
And that was phi of x. Phi of x is the probability amplitude for position.
That's right. That's right. If the argument, that's right. That's correct. Now, there is also a notion of an amplitude for finding different momenta, and I'll just remind you that's connected to Fourier transforms of psi of x. But I'm not going to do that now. If we need Fourier transforms, we'll come back to it. At the moment, Fourier transforms and the momentum representation. This is called the position representation. The representation of state vectors by psi of x's is called the position representation. There is also a momentum representation, but it will take us too far afield right now.
Question?
Yes.
What is the probability of the position? So in other words,
Psi star psi of x.
if the psi function, the wave function is the Dirac delta function, and what is it when you multiply that? When you get its probability, what does that look like?
It looks like the square of a delta function, which is just higher than the delta function, but it's concentrated at the origin. It's concentrated at the origin, and we have not talked about normalizing wave functions, making the area under here equal to 1. That's a thing that we want to do, and but as I said, I hesitate to go into any given thing too deeply because we'll wind up doing the whole class again. Yeah.
So these state vectors are all represented by column vectors. Is that it?
You can represent them by column vectors. In other words, but it'd be a little awkward to represent psi of x by a column vector. X takes on a continuous infinity of values, whereas the column vector is useful for a quantity which takes on some discrete set of values. So you can think of it formally in your head as some kind of continuous column vector. That's for the ket vectors, and the bra vectors you can think of as row vectors. Okay, but when we need that, I'll remind you. By then you will have gone back and studied the lecture notes, and you won't need it. Okay. Next thing, how do things change with time? Things do change with time. And the evolution of a system with time is a special case of transformations that you can do on the state of a system. That, of course, is also true in classical mechanics. the motion of the system is represented as a transformation in phase space, a transformation of the phase space position. In quantum mechanics, the evolution of a system is a special case of a transformation that you can do on the space of states, taking every state to some other state. And of course, the idea is very straightforward. If the state at one instant of time is some psi, at some later instant of time it is something else, and that something else is a transform or a transformation of the original psi. There are some rules in quantum mechanics about the nature of that transformation. Oh, that transformation depends on the amount of elapsed time. Okay? If the amount of elapsed time is very, very short, then you would expect this transformation to practically be the identity transfer. In fact, let's go back. If the amount of time that's elapsed is 0, then of course the transformation is completely trivial. It just gives back the same state. You can say in that case that the transformation was just the identity operation on the state vector. But more generally, the time evolution is characterized, or the time evolution operation, let's now call it operator. It is an operator in the sense of operators. It's an operator, but it's an operator which depends on the amount of elapsed time. So let's give it a name. It's usually called U. U stands for unitary, but we'll come back in a moment for what unitary means. And it's parameterized by an amount of elapsed time. And it's such that when it acts on a state at a given instant of time, it takes you to the state at an amount of time t later. So for example, if it acts on the state, whatever the state happens to be at time t equals 0, then it will give you psi at time t. It just updates the state. If it acts on some state which happens to represent things not at time 0, but let's say at time t1, then it takes you to the state at time t1 plus t. In other words, it represents the evolution of the system from t1 to t1 plus t. That's the notion of U. That's the notion of a time evolution operator. It's a linear operator, but it is not a Hermitian operator. What kind of operator is it? Well, now we need a postulate, and the postulate is, we can say the postulate very easily. It goes back to this minus first law of physics that I harp on all the time, that information is conserved. In quantum mechanics, what it means is that if you start with two vectors, two states, which are observably different, which cannot be confused, in other words, which are orthogonal, and you let both of them evolve, they will stay orthogonal. It will not happen that two states that are observably different will evolve into states which are not observably different. All right, so what that says is that orthogonal vectors remain orthogonal. In fact, you can do a little bit better. You can prove from that statement that the inner product between vectors is unchanged by time. Okay, so let me just explore that idea a little bit. Whatever U is, it preserves the relationships between pairs of vectors. So for example, if we start with psi and phi, two vectors, they may be orthogonal or they may not be orthogonal. If they're orthogonal, this inner product is 0. If they're not orthogonal, it is whatever it is. Okay. Then the postulate is that if we transform psi and we transform phi, now phi is a bra vector and it transforms with the Hermitian conjugate of u. That would be u dagger. So, phi. What this equation says is that the transform of psi, when you take its inner product with the transform of phi, is the same as the inner product of psi with phi in the beginning. It says that the inner products between vectors don't change with time. Okay. That can only be true for arbitrary pair of psi and phi if u dagger times u is the unit operator. And that's called a unitary operator. U dagger times u is the unit operator, or the identity operator, or just one. That's the notion of a unitary operator, and the time evolution. In fact, all transformations, all interesting transformations that you do on the space of states, and we're going to talk about others besides time evolution, all interesting transformations, ways of transforming vectors into other vectors, are unitary. U dagger u is equal to 1. It's different than saying u is equal to 1, of course. U is a unitary operator. All right, let's pursue it. Yeah.
Question?
Yeah.
The way you first said it is if psi and phi were orthogonal, they would remain orthogonal, but this is a stronger statement than that.
This is actually, it's not. You can prove that if u is a linear operator and it maintains orthogonality, then you can prove that it maintains all inner products.
But this is the time evolution of two systems with different states. Even if they're not orthogonal, the overlap is conserved or whatever.
That's right. That's right. And I said that's what you're saying is correct. But I would say it follows from if orthogonality is preserved with time, then it's possible to prove that inner products are preserved with time. That's a little exercise. First of all, think about it in just ordinary three-dimensional space. Supposing you have some operation on vectors, ordinary vectors, which preserves orthogonality. Okay, what kind of operators on pairs of vectors will preserve the fact that they're orthogonal? Rotations, right. Rotations also have the property that they preserve the inner products, or the dot products. It's the same mathematics. It's the same mathematics. So this is the definition of a unitary operator. There are many unitary operators. So there are many possible things that could represent the evolution of a system, but they're all unitary. Okay, let's...
Excuse me. What would be an example of non-unitary transformation?
Oh, Hermitian operators are usually not unitary, except that the momentum is not a unitary operator, the position is not a unitary operator. Okay, unitary operators are operators whose eigenvalues are phases. Everybody know what a phase means? An e to the I times a real number, a point on the unit circle. A phase represents, on the complex plane, a point on the unit circle. 1 is a point on the unit circle. I is a point on the unit circle. -1 and -I. 1 over the square root of 2 times 1 plus I is a phase. The unitary operators are the analogs for operators of phases. Their eigenvalues are all phases. So if I have a unitary operator and I look at its eigenvalues, they will be points sprinkled around on the unit circle. That's why they're called unitary, because in some sense their length or the magnitude of their eigenvalues is unit. Okay, now let's see what more we can learn about u from making some reasonable assumptions. The first reasonable assumption is that if t is equal to 0, then u is just equal to 1. All it says is that if you don't allow any time to elapse the vector just comes back to itself, and u is equal to the unit operator. So u of 0 is equal to I, the identity operator, the operator whose matrix representation is just 1 along the diagonals. It's just the operator which does nothing, it just takes the thing back to itself. Now, is u unitary? Sure it is. The Hermitian conjugate of u is the Hermitian conjugate of the identity operator, which is just the identity operator itself. And identity times identity is just identity. So yes, 1 is 1, or the unit operator is unitary. And it's the time evolution when no evolution happens. Okay, what about evolution by a very, very small amount of time? Okay, so let's, instead of writing u of 0, let's write u of epsilon. Take u of epsilon, it is not 1, so something happens over time evolution, but it is close to 1. It's close to 1. That, of course, is an assumption. That's the assumption that systems evolve continuously, that they don't make radical jumps over very, very short periods of time. And it is an assumption. It's an assumption, ultimately, which is justified by experiment. So that says that u of a small time epsilon, if we were to expand it in small epsilon, would be 1 plus something proportional to epsilon times an operator which is a finite operator. The smallness of epsilon is represented by epsilon here, times something which I'll temporarily call h, but it's a wrong identification. In a minute we're going to change it. Let me not call it H. What's another letter? Give me another letter, quick. No. G. F, G, H. Yeah, G, good. All right, so U is of this form. There's nothing wrong with this. This is a correct thing. The only question is, what do we know about G? So let's write down U conjugate, Hermitian conjugate of epsilon. That's equal to 1 plus epsilon times G conjugate, the Hermitian conjugate of G. And now let's multiply these together and insist that the answer to leading order in epsilon is just 1. Okay, so that will say that 1 plus epsilon G dagger times 1 plus epsilon G is equal to 1. Looks a little queer. 1 times 1 is 1. So what's left over? What's left over is epsilon times G dagger plus G. And that must be 0. To order epsilon, working to order epsilon, the condition that U is unitary is the condition that G plus its own Hermitian conjugate is equal to 0. In other words, getting rid of the epsilon, that the conjugate of G is equal to minus G itself. Operators with this peculiar property, do you know numbers that have that property? You know any number that has the property that it's minus its own complex conjugate? It is true, but there's a wider class of them. Pure imaginary things. So this is the analog of G being pure imaginary. If we multiply it by I, it becomes Hermitian. This is called anti-Hermitian. Hermitian is when G dagger equals G. Did we write that someplace? Yeah. A equals A dagger is unobservable. G dagger equals minus G. We can fix that very simply. Just define G dagger to be, now do I want plus or minus? I always forget. It always takes me a minute or two to, I wanted to write 1 plus I epsilon H. But I think the right answer is minus. Whether you put a plus sign or a minus sign here is a convention, complete convention. It defines H. This one becomes 1 plus I epsilon H, H dagger. And the condition just becomes that H equals H dagger. In other words, if I put a minus I epsilon H, no, plus I epsilon H dagger, minus I epsilon H, then the condition that U is unitary is just the condition that H is Hermitian. In other words, that H is an observable. Yeah.
What assumption are we making that allows us to ignore the epsilon squared term?
Well, we're just working to order epsilon. We could work to order epsilon squared, but then we would have to be consistent about it and put an epsilon squared term in here. The epsilon squared term that we would want to put in here would be minus epsilon squared over 2 times H squared, and but we consistently work to 1 power in epsilon and assume that epsilon is small enough that we can ignore epsilon squared. We can do that consistently. We've done it over and over and over. But then you're perfectly right. We do have to come back and check that the formulas make sense to higher order, and they do. I'll discuss that a little bit. But working systematically to order epsilon and dropping anything of higher order in epsilon.
I just wondered if we were following the details of it, we have to say that H is approximately Hermitian or something like that.
Yes. No, well, okay. With this definition, you would say H is approximately Hermitian, but notice that epsilon factors out of both sides of this equation. So once it's factored out, it just says that H. No, I think the thing which is approximate is this relationship here. Yeah. And I'll come back and tell you what to do I'll tell you the right formula in a little while at some point. Okay, so what do we learn? We learn that the unitary time evolution, which contains a U of t, also is specified in terms of a certain observable that I've called H. H stands for Hamiltonian. It also stands for Hermitian, but it stands for Hamiltonian. It is the Hamiltonian of quantum mechanics. And so we come to the conclusion that there exists an H, we will call it the Hamiltonian, and it is related to the time evolution for small time intervals by 1 minus I epsilon H. What is the general equation if epsilon is not small? Incidentally, if epsilon is not small, we might want to call it T. We might give up calling it epsilon. Epsilon is usually reserved for a very small quantity. We might try writing U of T, but this wouldn't be right for large times. It wouldn't be large for large times. Let's see if we can improve it a little bit. Well, you know, I think I won't spend time at it. I will just tell you the answer. The answer is that this really should be written as e to the I h t. Now, why do I? Let me just say a word or two about exponentials. If you have an exponential e to some small number, and let's just call the small number epsilon, where epsilon is small, times an ordinary number, and let me call the ordinary number little h. Epsilon times h is a small number. Okay. For very small epsilon, e to the epsilon h is 1 plus epsilon h. Does everybody know that? That's the formal Taylor series expansion of keeping only the first term, assuming the second term and higher terms are negligible. Okay? Now, supposing you want to make epsilon a little bigger. instead of just epsilon, I want to take e to the 2 epsilon times h. E to the 2 epsilon times h is just the square of e to the epsilon h. E to the 2 times something is just the square, so it's equal to 1 plus epsilon h squared. Supposing you do this over and over and over, which incidentally is equal to 1 plus 2 epsilon h plus epsilon squared h squared. But this is still an approximation. This was an approximation to this. This is still an approximation to this. Here's a theorem that if you do this over and over enough times, let's say n times, e to the epsilon times n times h, such that epsilon times n is finite. In other words, epsilon times n, epsilon is an infinitesimally small number, but I do it enough times so that n times epsilon is a finite number, namely t. I do this over and over. What happens? Excuse me, let me go back. Let's do it this way. 1 plus epsilon h, and I do this a number of times, a large number of times n, such that n times epsilon equals t. What do I get? Anybody know? It's a binomial expansion, but it's also a construction of the exponential function. It's a rigorous theorem that as epsilon gets small and n gets large, in such a way that n times epsilon is kept fixed, this just becomes e to the ht. Say it again. One person talk. I think it's right. I think it's right. Right. And the way you can just understand it is by saying that for small epsilon, 1 plus epsilon h is the same as e to the epsilon h. And if you take it to the nth power, the epsilon just multiplies the n and becomes t. Okay, so I will tell you right now the generalization of this for finite times 1, there should be a minus sign here, 1 minus IHT for finite t really becomes e to the minus IHT. And this is an important fact, but for small intervals, small epsilon, we can just be consistent and work to order epsilon. We'll find out everything we need to know. Okay, so there's a concept now of a Hamiltonian. Let's see if we can understand this equation a little bit better. Let's take the wave function psi, or the state vector psi, at a time t plus epsilon. I'm starting at time t with a certain wave function, and I'm allowing it to change over a tiny time interval. What is the answer to this? The answer to this is that it is equal to e to the I h epsilon times psi at time t. Now let's just see what I did. Minus or plus? Sorry, minus here. Starting at time t, let's update by a small little time epsilon. The rule is we multiply by u of t, u of epsilon. We're updating by an amount of time epsilon, and that's equivalent to multiplying by e to the minus I h epsilon times psi of t. So this is the rule for going from a time to a neighboring time. But now let's write that out as 1 minus IH epsilon times psi of t. And let's write this side, I'm not going to forget the, okay. Yeah, okay, yeah, let's put them in. And this one here is psi of t plus epsilon. Now let's multiply out. 1 times psi of t is psi of t, but let's take that over to the left-hand side. That'll give us psi of t plus epsilon minus psi of t. Just a term coming from 1. The term coming from 1 will give us the difference between psi of t plus epsilon minus psi of t. You see where we're going. We're building a differential equation for psi. Psi of t plus epsilon minus psi of t is just equal to minus IH epsilon psi of t. And finally, divide by epsilon. Okay, what's the left-hand side? The left-hand side is the time derivative of the state vector psi. And the right-hand side is just minus IH psi of t. Okay, so that leads us finally to the Schrodinger equation. The Schrodinger equation says that the psi by dt, this could be a wave function or it could be the state vector. I will leave the notation a little bit abused. I won't bother writing the ket vector here. It stands for both the equation for the state vector or the equation for the wave function itself. The psi by dt is equal to minus I h psi. If you want to put vectors in, if you want to turn it into an equation for a state vector, you put ket notations there. Otherwise, it's just the equation for a wave function. This is the Schrodinger equation. This is the time-dependent Schrodinger equation. Okay, this is Schrodinger equation, time-dependent, the TDSE, time-dependent Schrodinger equation. And what it tells you is how the state vector changes as a function of time if you are so lucky to know what the Hamiltonian is. Hamiltonian is a Hermitian operator, and you can make all kinds of quantum mechanical systems just to play with by choosing different H's. We did this last quarter. Okay, what about the time-independent Schrodinger equation? The time-independent Schrodinger equation is just the statement that H is a Hermitian operator. It has eigenvalues, it has eigenvectors. Its eigenvalues are the observable values that you would get if you measured H. And what are they called? They have another name. Energy levels. Energy levels. Incidentally, I promised you that I would keep around Planck's constant, and I've already dropped it. It goes over here. It goes over there. I don't promise by any means that I will be consistent about Planck's constant. Yes, I will be completely consistent by choosing Planck's constant to always be equal to 1. Sometimes I'll put it in, sometimes I won't put it in, but I will never confuse it with I or the square root of 2. Okay, so that's the time-dependent. The time-independent Schrodinger equation, that's just the eigenvalue equation for the eigenvalues of H. And all it says is that H on an eigenvector of the energy, a state with definite energy, is equal to E times the energy, E being the eigenvalue of H. E being the eigenvalue of H. So this equation here is the equation which tells you how to find the states and the values of energy that go with them that correspond to states of definite energy. You solve this equation, and it gives you a whole bunch of possible eigenvalues and eigenvectors. Those are the eigenvectors and eigenvalues of the energy operator. Okay? And again, we went through this. We did some examples last 2 quarters ago. On the other hand, this equation tells you how the state vector changes with time. And as you can see, it's the same h on in both equations. So the question of the energy levels of a system are intimately bound up with the way that the system changes with time. Okay, so good. And that's quantum mechanics in I said before it was quantum mechanics in a nutshell. Well, it's a slightly bigger nut, but that's it. That's what you need to know. That's a summary of a quarter's worth of quantum mechanics that we did. Any questions?
Can you, if in the time-dependent equation,
This is the time-independent Schrodinger equation.
if in the time-dependent Schrodinger equation you replace psi with E?
Psi with E?
Yeah, can you do? Yeah,
Yes.
then you can drop the ket things, right? Then it becomes just an differential equation, because H times E will be just E times E.
No, we don't want to drop the ket symbol. Leave the ket symbol there. Leave the ket symbol there for the moment. What we can do is we can ask how a eigenvector changes with time. That we can do. So we can plug in here and we can ask how the eigenvector changes with time, and the answer is that the eigenvector will change with time by just multiplying it by I times the energy level. That's what tells us how eigenvectors change with time. Anybody remember the answer, how an eigenvector changes with time? It just gets multiplied by e to the I times the energy times time. Okay, so that we can go through that. We don't need... It's in the notes. Go back to it and check it out. All right, now, the time evolution is one example of transformations that you can do on a system which preserve certain facts about the system, in particular which preserve the inner products between vectors. In other words, which preserve the logical relationships between vectors, preserve the notion of orthogonality, preserve the notion of vectors being the same vectors, and that kind of... There are many other kinds of transformations that you may want to do on a system. In particular, among them are symmetry transformations. We will need to talk about symmetry transformations. Now, I will tell you where we're going. One of the most important symmetries of nature that occur over and over and over again in all sorts of contexts, but in particular in the theory of atoms, is rotational symmetry. An atom, in particular a hydrogen atom is an electron moving in a central force field. The equations of a hydrogen atom are rotationally symmetric, and that's because the potential energy, the Coulomb potential, is rotationally symmetric. It's a central force. And so hydrogen atoms, and basically all systems in nature really, but hydrogen atoms in particular, enjoy rotational symmetry. If you rotate, all it means is that if you rotate your coordinates, the description of the hydrogen atom doesn't change. Or another way to say it is if you rotate the hydrogen atom, it's still a hydrogen atom. It may or may not be the same state, but it's still a hydrogen atom described by the same set of equations. So the notion of a symmetry is central in quantum mechanics. It is also in classical mechanics, but it comes up and really hits you over the head in quantum mechanics. And we need to explore a largely for the purposes of understanding rotational symmetry, we need to understand the concept of a symmetry. So I'm going to spend 15 minutes explaining exactly what a symmetry is. Keep in mind, if you want to keep one in mind, there are two that you can keep in mind for just to have something in your head. One of them is rotation symmetry, where it just says that if you take a system which satisfies a certain set of equations and you rotate it, physically rotate it about an axis, you may or may not change it. I can tell you this, if you rotate me, you'll change me, right? Yeah, you will. If the Earth weren't here and I was in outer space and free space, then the Leonard equation, whatever the equation governing me is, would be the same for the rotated or the unrotated. Another way of saying it is I couldn't tell whether I was rotated or not. If you rotate me and then just go away, I can't tell that I was rotated because the equations that govern my metabolism, my internal structure, and so forth are exactly the same as had I not been rotated. Okay, so rotation symmetry is one example. Another example is translation symmetry. If you take me in outer space and you set me down and you say, how do I feel? I feel fine. You take the same state, but you translate me over by a meter, and you ask me how I feel, I say exactly the same as I felt before. It's a symmetry. On the other hand, there are situations where translations may not be a symmetry. You know, if there was a furnace over there, a fire, hot fire, and you put me over here, and you said, how do you feel? I feel fine. Now translate me over to here, how do you feel? Well, I don't feel so fine. So the presence of an object may break translation symmetry. On the other hand, if you think about it a minute, wait a minute, what if I really translate everything, me and the furnace? Then we restore the translation symmetry. So symmetries are operations, or there are operations that you can do on states of systems, and if the operation doesn't change the equations, doesn't change the properties of the system, doesn't change the way you describe the system, then that transformation is called a symmetry. For a free particle, for any ordinary system, if it's out in outer space, far from anything else, and you translate it, that's a symmetry. You rotate it, that's a symmetry. What if you squeeze it? Change its dimensions by squeezing it. That's generally not a symmetry. You know, if you take a crystal of rock salt or something and you squeeze down on it and compress it by a factor of 2, it doesn't behave the same way. So there are all kinds of things which are not symmetries. Nevertheless, they still may be operations that you can define, but they may not be symmetries. Okay, let's talk about the condition. Let's first of all try to quantify that idea. We have states. The generic or typical state of the system that we're interested in is called psi. We're going to do an operation on it. That operation might correspond to rotating the system, it might correspond to translating the system, or it might correspond to something uglier than that, like squeezing it or stretching it, but doing something to it. And let's represent that by an operator V. I use V because I've already used U, but I intend it to be a unitary operator. Why a unitary operator? Well, if I really have a symmetry, and I have two states which are different than each other, I apply the symmetry operation, I expect them to stay different. If there are two states of me, happy me and sad me, they're different from each other. They're observably different. There's an observable that you can measure, the happiness operator, and they're different. If you then rotate the state out in outer space, the distinction should remain. So that means that orthogonal states should remain orthogonal when you do a symmetry operation, and that says that the operator V should be unitary. So V is unitary, and it represents dagger v equals 1. I don't use u because I'm saving u for the special case of time translation, of evolution. Okay, now let's suppose, this is a little bit tricky, so there's u's and there's v's, and it's quite tricky. It takes me half an hour each time I try to do this to get it right, but it's also very, very simple. Okay, let's suppose that a wave function or a state vector, I'll use them interchangeably, let's call it psi1, under time evolution becomes psi2. If I take psi1 and I allow it to evolve with time, let's represent that by putting a little u here. U represents time evolution. V does not. V is something else. And if I take psi1 and allow it to evolve for a certain amount of time, it will become psi2. Okay, so that's under u. Another way to say that over here is that u on psi1 is equal to psi2. That's all. Evolve psi1 for a little bit of time, and you get psi2. Okay. Now let's imagine the transformed version of this. Transformed, it could be by rotation, it could be by translation, by some symmetry operation. What does this equation say for the transformed things? Well, let's call this psi prime. Now there are too many. Let's keep in mind exactly what's going on here. 1 and 2 represent some initial state and some final state. Evolution from one to another. Prime and unprimed represent the action of the symmetry operation, which could be rotation. Could be rotation or it could be translation. Okay, here's what I maintain. If there really is a symmetry, then psi1 prime, if we were talking about rotations, then psi1 prime is just the rotated state of psi1. Psi1 prime will evolve to the rotated version of psi2. Let's see what that says, okay? If I evolve myself over a period of time, and I'm in some state, and I get some other state, I go from happy to not so happy, then when I rotate myself, I should also find under the same evolution that I go from the rotated happy state to the rotated not so happy state. That's what it really means to have a symmetry. That the evolution of the transformed state behaves the same way as the original state. It's a little bit tricky. Okay, let's see if we can make an equation out of this now. Yeah, okay. So the first row here is just the equation that psi2 is u psi1. That's what this says. The second equation, let's go to the second equation. To go from unprimed to prime, you multiply by v. So the second equation here says that v, it says that, I'm sorry, this always confuses me. It says that psi2 prime is equal to u times psi1 prime. To go from 1 to 2 is time evolution. To go from unprimed to prime is v, is the symmetry operation. All right, so psi1 prime is v times psi1. All right. So we have u v times psi 2 is u times psi 1 prime, and psi 1 prime is v times psi 1. Okay, that's the right-hand side. The left-hand side is v on psi 2, but psi 2 is u times psi 1. So after perpetual confusion that it stumps me every time I try to do this on the blackboard, what it says is that if a thing is a symmetry, in other words, if it preserves the way evolution takes place, if it's a transformation which preserves the time relationships between vectors, then it says that v times u must be equal to u times v. This, of course, must be true for every state if it's to be a true symmetry of nature. A true symmetry of nature, rotation symmetry, for example, is not something which only applies if I'm standing vertically upright. It should apply to any particular state of the system. And so if v times u on any psi 1 is equal to u times v on any psi 1, what it says is that symmetries of nature are such, they're operations, they're v's, unitary operators, which commute with the time evolution operator. For all? Yes, in fact, for all time. We'll see, it's enough for it to be true for one time, and it will be true for all time. But yes, that's correct. Okay, so unitary operations, things you can do to the state vectors which preserve orthogonality, which commute with the time evolution operator, are symmetries that preserve the evolutionary relationships.
So physically, you're saying you can rotate and then wait, or you can wait and then rotate.
Exactly. The words are very simple and they make perfect sense, and yes, that's exactly what it says. Okay, so how do we identify symmetries? We look for operations which commute with a time evolution operator. Now, remember that the time evolution operator is itself, let's take the limit of a small time evolution just to analyze it a little bit. This says, or first of all, it says that v times 1 plus I epsilon h, 1 minus I epsilon h, 1 minus I epsilon h, is equal to 1 minus I epsilon h, this is the first order again, times v. I'm just expanding it out. The first order is good enough. It gives us everything we really want to know. First of all, v times 1 is equal to 1 times v, so those cancel. And what it says is that minus I epsilon vh equals minus I epsilon hv. Well, canceling out the minus I epsilon, it says that v commutes with the Hamiltonian. Okay, let's cancel out these things. The minus I epsilons. A symmetry is a unitary operation which commutes with the Hamiltonian. Any unitary operation which commutes with the Hamiltonian is a symmetry, and any symmetry is a unitary operation which commutes with the Hamiltonian. That's very abstract. It's extremely abstract, and in order to appreciate it, we have to do a couple of examples. We'll do some examples in a moment, but let's just focus on that unitary operations on the space of states which commute with the Hamiltonian are symmetries.
What limited us to unitary?
What's that?
What limited V to being unitary?
What limits? Sorry.
What requires that V is unitary?
Oh, yeah. A symmetry, whatever a symmetry is, it preserves logical relationships between the vectors. So it's an assumption. It's an assumption that the symmetries of nature take orthogonal states to orthogonal states. Okay. That seems plausible. A symmetry should not take two states which are distinctly different from each other and act on them to give states which are not distinctly different from each other. You wouldn't call that a symmetry. Yeah, mutually exclusive things should stay mutually exclusive. Right. Okay, so we now have an abstract mathematical definition of any symmetry operator, of any symmetry. This will become much clearer when we do some examples. Symmetry, commutator of H with V is equal to 0. That's what it says. Do you remember from 2 quarters ago what the commutator of a thing with the Hamiltonian is? The time derivative of it. Yeah. So what this says is that whatever the operator V is, it's conserved. Conservation of a certain quantity, in this case V, meaning that it commutes with a Hamiltonian, is the same as saying there's a symmetry. You've seen this before in classical mechanics. What's the connection between symmetries and conservation laws called in classical mechanics? It's called Noether's theorem, right? It's much simpler in quantum mechanics. It's much simpler in quantum mechanics. We don't need any fancy Lagrangian or anything else. All we need to know is that time evolution commutes with the symmetry operation itself. And that can be read in 2 different ways. It can say that doing the symmetry operation, well, it says what it says. It can be read 2 different ways, but they both say the same thing. Okay, so now let's go one step further. There are different kinds of symmetries. Let me give you some examples of 2 different kinds of symmetries. There are discrete symmetries and there are continuous symmetries. Let me give you an example of a discrete symmetry. Think about reflection in a mirror. Reflection in a mirror takes a right hand to a left hand. Okay. That's the mirror image of a left hand as a right hand. That's a discrete operation. It takes left to right, but there's nothing sort of in between. It's just a discrete operation, left to right. Let me give you another example of a discrete operation. Suppose we have a pair of electrons, or a pair of particles. A pair of particles, and they happen to be the same kind of particle. A pair of electrons or a pair of protons. Then if I take the 2 particles and I interchange them, whatever the state is, I interchange one particle with the other particle. That's a symmetry. Why? Because the particles are of exactly the same kind. A proton over here and a proton over here is the same as a proton over here and a proton over here. That's just interchange of them. Those are discrete operations. Discrete operations means that there's sort of nothing in between. Or let's say heads and tails. Just say heads and tails, a head and a tail. If the coin happens to have no markings on it, whether it's heads or tails, and you turn it over, then the physics of a coin and the flipped coin are exactly the same. Those are discrete operations. By discrete, I mean in distinction to continuous operations, and continuous operations are like rotation in space. Rotation in space, you can do a very small rotation. Small means one by a very small angle. In fact, you can go further. You can say that every rotation about an axis can be built up by tiny rotations about that same axis. That means that the rotations have a continuity to them that the flip of a coin does not have. Flip of a coin is either its heads or its tails, and there's nothing in between for classical coins. For systems in three-dimensional space, you can, or two-dimensional space for that matter, you can rotate them. You can rotate them by 90 degrees. That's a transformation. But you can build up that 90-degree rotations by lots of little infinitesimal transformations. Those are called continuous symmetries. What about translation symmetry? Is translation symmetry continuous or discrete? Well, it's continuous. You can take any translation of a system and think of it as being compounded out of lots of small translations. The continuous symmetries are the ones, and in particular the rotation symmetries and translation symmetries, are the ones I want to focus on. Okay? What do we know about continuous symmetries? We know we can build them out of lots of little elementary small transformations. So let's focus on the small transformations. We're going through basically the same manipulations that we went through over here. Time translation is a continuous thing. You can build up a time translation by 10 seconds by thinking of it as lots of little time translations by microseconds. Okay? And that led us to the conclusion that U's are related to Hermitian operators through this relationship here. Exactly the same is true of every continuous symmetry. Exactly the same thing is true. Every continuous symmetry can be thought of as being built up by little infinitesimal ones, which have the form 1 minus I epsilon, not times a Hamiltonian, but something, some Hermitian operator. Let's call it G. G stands for generator. G stands for generator, and what we're thinking about now is a symmetry transformation, but one of them which is very close to being the identity. Such a transformation can always be represented as something close to the unit operator, and close to the unit operator means just shifted by a small amount. By the same argument that told us that H is Hermitian, G is also Hermitian. Symmetry operations, which are continuous, can be represented in terms of infinitesimal transformations which are generated by a generator G. And if we plug this into here, and we then write the commutator of H with 1 minus I epsilon G is equal to 0, what does that say? What's the commutator of H with 1? Commutator with anything with 1 is 0. Everything commutes with the operator 0. The I epsilon, that factors out, and what it tells us is that symmetry operations are generated by, this is what it means to be generated by. Generated by means can be built up by lots of little ones. They're generated by things which commute with the Hamiltonian. So, if you want to find all of the symmetries of a problem, you'll start looking around for all the things which commute with the Hamiltonian. There's another feature of things which commute with the Hamiltonian. Do you remember from last quarter? It's true both in, what was that? They're conserved. So, conservation and symmetry are closely connected. If you want to find all of the symmetries of a problem, it's equivalent to finding all the things which are conserved. All right, now this was very abstract, and so we need to do an example or two to get the idea. Let's do an example, and let's begin with translation. Translation of a particle from one place to another. Okay. Translation of a wave function. We want to take a wave function. Here's a wave function, and we're going to move it a little bit. We're going to translate it to a new wave function. and we want to find out what operation does that. If we have a psi of x, what operation do we do to translate it to a new position? We're going to take that new position to only deviate by a small amount, by amount epsilon, but we know what the answer is. The answer is psi of x goes to psi of x plus epsilon. Epsilon now could be a large number. We're just translating by a large number, but specifically I want to think about the case of a small translation. Translation by a little bit. Okay. So, psi of x, in other words, we can write that the translated wave function, in fact, we can write it this way. Whatever v is, we haven't figured out what v is yet, but whatever v is, it acts on psi of x to give us psi of x plus epsilon. That's pretty easy. That's what a v is. That's what the v does in this case. It acts on psi of x, and it translates the wave function by amount epsilon. Okay. Now, if epsilon is small, we can also write that this is equal to psi of x plus the derivative of psi with respect to x times epsilon. So, what v does, what v on psi does, is it gives back the same psi plus something proportional to the derivative. That it proves that whatever v is it's the unit operator. That's the first term here. It acts on psi of x to give back psi of x plus a small change, and the small change is epsilon times the derivative operation. I haven't written on x, we could write on x times psi. V is an operator. It's the unit operator plus epsilon times the derivative operator. We can act on any wave function, and what it will give us is the wave function infinitesimally displaced. Okay. Now, what about d psi by dx? What about d by dx? d by dx is an operator. It operates on wave functions. It's a linear operator. Right? It's connected with the momentum operator. Remember the relationship. The momentum operator P equals minus I h bar d by dx. All right, so what do we want to do? We want to write, let's multiply by I, get rid of the I here, and divide by h bar. Differentiation is I over h bar times momentum. So let's write this that way. 1 plus epsilon, I epsilon over h bar times the momentum. We now have an example of a infinitesimal symmetry operation. By infinitesimal, I mean just by a little bit of a shift. And we found out what its generator is, the G. Where was it? Did we have G here? No. Yeah. V is 1 minus I epsilon G. In this case, I would have much preferred that I defined things so that this came out to be minus here, but
What's the minus sign?
To the momentum definition. Yeah. The momentum definition.
Yeah, further
Oh.
to the right, further to the right.
Upper right.
Upper right.
yeah, this one, I think that's right.
The minus sign.
No, that's right. You think this is wrong? It's right, right? So, let's see. So, I substituted. I think I got this right. Wait, sorry, did I? Yeah, that's right. Do you disagree with this? No, I think it's right. All right. Now, I think if I shift the wave function to the right, that's really putting a minus sign here. Yeah, I made a mistake in defining a shift to the right. A shift, it looks like it should be x plus epsilon, but psi of x goes to psi of x minus epsilon. So this is actually a minus sign here. If you track that through, we will find out that there's a minus sign here. Yeah. Okay, so it identifies for us what the symmetry generator G is for translations. And what is it? It's the momentum divided by Planck's constant. Right? Momentum divided by Planck's constant, we can write that the generator of translations, here's the language, the generator of X translation is P sub X. P sub X, strictly speaking, divided by Planck's constant. We can drop the Planck's constant. I will drop the Planck's constant. And as a matter of fact, the definition, the official definition, really doesn't have the Planck's constant in it. But there's an example. P of X. Now, is P of X, is the momentum along the x-axis conserved? Depends on the Hamiltonian. It depends on the Hamiltonian. So let's write down a Hamiltonian. The Hamiltonian for a free particle, a particle moving in empty space with no forces acting on it, H, in that case, is just P squared over 2m. The momentum squared divided by twice the mass. If this is a one-dimensional problem, then it really is just px, just the x component of momentum. Does the Hamiltonian commute with px? Well, that becomes equivalent to the question of whether px commutes with px squared. Yes, every operator commutes with every function of itself. P of x commutes with P of x squared, it commutes with P of x cubed, it commutes with any function of P of x. So, for a free particle moving along the x-axis, we first of all find that the momentum is conserved, and of course, we also have a translation symmetry. The translation symmetry is just the fact that the free particle will behave the same way wherever you start it. If you start it here and it gets to here, then if you change the starting point, everything will just translate. Okay, so that's an example. P is both a conserved quantity and the generator of translations. What if there are more directions of space? If there are more directions of space, then there are several symmetries. You can translate along the x-axis, you can translate along the y-axis, you can translate along the z-axis. In that case, the Hamiltonian becomes px squared plus py squared over 2m plus pz squared over 2m. And the translation symmetry along the x-axis is still just px. Translation along the y-axis, the generator is py, and so forth. And each of them commutes with the Hamiltonian. So this is an example of the connection between symmetries and conservation laws, which is very simple. The next time, it looks like we're about out of time, the next time we will do rotation symmetry. Rotation symmetry is much more interesting, it's much more involved, and it will bring us to the subject of group theory. There's some group theory here, but the group theory is completely trivial. The next time we will talk about rotations in space. And what's interesting about rotations in space is they don't commute with each other. A rotation about x followed by a rotation by y is not the same as a rotation by y, rotation by x. And that will give us the idea of non-commuting symmetries. Symmetries, collections of symmetries which don't commute with each other, and when we find those, they have power. They have real power to tell us about all kinds of physical properties of a system. Okay, so next time, rotation symmetry.
For more, please visit us at stanford.edu.